So the previous video was about drivers and APIs, and I was focusing on a certain problem that users had reported. It actually wasn't in the notes of the release notes of the recent driver, but users have reported that there is some microstuttering and sometimes crashing in Vulkan games using multi-monitor setups. Now I do have a multi-monitor setup, and so I decided to benchmark a suite of games in hopes that I could recreate this issue. I failed spectacularly. So because my reasoning was wrong, I thought that if I did an unrealistic scenario, like with my 5090, using DLSS performance mode, in 4K, benchmarking these games like that, they would then downscale to 1080p and then up render to 4K. And I thought that that would increase the load on the CPU, which it often does, and I saw that in my testing, but that it would tax the rendering pipeline. And it turns out I was wrong. I mean, that's not really what happens. What happens is that extra workload for rendering up on 1080p image is just done by your tensor cores. That's just your AI. So it's not a situation that would be useful for testing an API and driver interaction, which, to be perfectly honest, I don't have a granular enough knowledge base to be able to effectively test something like that. And, you know, you can roll back a driver, but you can't roll back an API. So I had some incorrect assumptions about DLSS, and then I had benchmarked a lot of games using those settings, those unrealistic user scenarios, but for a purpose. Anyway, what I ended up doing was introducing a bit of stutter in some of these benchmarks, and that got me thinking about stutter. So let's talk about stutter. Okay, I fixed the annoyingly sensitive autofocus issue on my camera, so please forgive that. First, I just want to talk about real quick. Actually, let me talk about what the methodology for the method of benchmarking on this channel is going to be. Here's some graphs. Obviously, the big one is your average FPS. The orange one is your 1% lows, and the green one is your delta between the two. Obviously, the top and bottom row combine for the same amount of frames as the top and middle row combine for the same amount of frames as the bottom one. But I like to see this delta. I always like to see this delta. So for example, what I'm looking at right now does not perform nearly as well as this one. This is Red Dead Redemption 2. I tested in Vulkan with those silly settings that I mentioned earlier, and that is a 26% delta as percentage of average FPS, which is how I measure things. This is the blue is your average FPS, the orange is your 1% lows, and the green is the delta between the two. And you want that green to be as low as possible. What we did, and this is what's so interesting, one of the things that was so interesting about these benchmarks, which again failed for the specific intention, but by creating this microstuttering issue by the intentional misuse of DLSS, which incidentally, really, the reason that you can sometimes get visual glitches and microstutters when using DLSS performance mode is because it's so aggressive at 4K. That's basically the only reason. It's downscaling all the way to 1080p and then up to 4K, and that aggressive process can cause some artifacts, some stutters, particularly when there's lots of textures or in fast-moving scenes. So that's the reason for that. It's the reason why I saw some stuttering and some pretty bad deltas. So when I talk about deltas on this channel, I want you to know what I mean by that and why I focus on that. I focus on the delta between 1% lows and average FPS, because that is a frame time spike, and I'm going to get into an illustration of that next. But I wanted you to know that because that is the microstuttering, okay? That's what it is. It manifests in frame time spikes. That's all microstutters are. And we're going to talk about frame times in a second. Before we do, though, this was the most fascinating thing that I found out in this testing. I am so pleased I discovered this. I did not really understand this. So in Shadow of the Tomb Raider, this right here was the DirectX 12 testing that I did in the high preset, again using DLSS. But this does not have the ultra ray trace shadows. So Shadow of the Tomb Raider kind of does a partial implementation of ray tracing where you can turn it on for, by the way, I say it's on there, but I know that it's not. There's no ray tracing there, so let me go ahead and get rid of that. But yeah, so this is with DLSS on highest preset, and you're seeing about a 36% delta as percentage of average FPS, which I don't like so much, but couple stutter, a little bit of stuttering you might get there, not too bad. But look what happens when you do ultra ray trace shadows. Same game. Look at that. Look, it smooths the experience significantly. And we're going not that far down in average FPS. We're going from about 270 frames to about 204. Now that seems like a lot, but if you look at these 1% lows, I mean, it's right on their heels. 168 1% lows, and then 170 when it was 270 frames. So that 1% lows didn't move. And the only thing that moves was the FPS, and who cares? It's a single player game, so who gives a shit about FPS? What you want is that delta to be as small as possible in a game like this. And ray tracing doesn't just make it pretty, it smooths your frame time. So let's talk about frame time. Okay, so the point I wanted to impress about this is just some stock image. We've all seen something like this, RTSS OSD. You get with your Riva tuner, you run with MSI. So here's the point I want to impress about this. This number right here, this 13.8 milliseconds, is really, first of all, you don't even need your FPS counter to determine FPS from this number, but you can kind of guesstimate what your 1%, if all you had was this graph right here, then you could probably guess, or approximate pretty well even the 1% lows. And you would know for certain your FPS because you have a constant in the formula, which is 1000, 1000, which is how many milliseconds are in a second. 1000 milliseconds equals 1 second. You can divide that by your FPS, or you say, like, take, say, 240, which is my refresh rate, and that gives you 4.17, and this guy had 13.8. So just, substitute, divide from the other side of the equation. So now that 1 second gets divided by 13.8, and that gives you 72 frames per second. So the reason that I think it's helpful to think about things from the perspective of deltas, from the perspective of frame time spikes, is because what is a frame time spike? Well, let's say you got this graph here, and this line here it's moving to its left, as you're playing a game, and you're seeing these little bumps here in the road, and then it's just nice and smooth, and then boom, there's one that goes up like that, and then there's a few little bumps, and then boom, there's another one that goes up like that. Well, let's say it bumped up here to 40, And then you just take your 1000 milliseconds, and you divide that by 40 and you get 25. 25 FPS is unplayable if the whole game was 25. So when it switches from, was that 72 FPS to 25, that's a major frame time spike, and you will notice that. It'll be a hitch, it'll be a little glitch, it'll be a microstutter. So what is microstutter? Microstutter is rapid increase frame times in frame time increase in a frame time spike means a rapid reduction in rendering time of the frame. So it spikes like inversely proportional to your FPS, and that is what a microstutter is. That's the definition of it. You cannot address microstuttering unless you know what it is. You got to know how to see it. You got to know how to verify that that is the problem. And then, unfortunately, once you see it, you can't unsee it. And then you will see it every single time. And then you will be driven by an insatiable need to try to fix every single little microstutter. Now, we're running a Red Dead Redemption benchmark. I always get microstuttering in this scene right here, although fewer and fewer stutters, because VNG sync is enabled in the NVIDIA control panel, ambient occlusion is off, DLSS is off. We've done everything we can to protect against the microstuttering, but I'm going to show you how to see it. Once you think you see a stutter, and I don't think I need to describe what a stutter is, you're going to go ahead and look up here at the frame time, the graph right there, to see the spike, and that will confirm that you've seen a stutter. So you usually get a couple of them. There was a little one right there. And we're watching carefully. Stutter. Yep, you just saw it. You just saw it sort of disappearing from the graph right there. So that's how you recognize them. Monitor with RTSS. There was another one. And the frame time graph turned on. And then you just watch and watch carefully. And when you see it, when you think you see it, just glance up at the graph. Oh, I didn't see that one because I was looking at the graph, but there was one. And verify it with the frame time spike. Now, as I said, we have tried to optimize the graphics settings against microstuttering, doing what we can to remedy the stutters with just the graphics settings, so that the few frame time spikes, and I didn't see any in the other scenes in this benchmark, but the few you see in this scene are the few that are remaining. And now we're going to look at some other methods for dealing with those occasional microstutters. So what I found so interesting about working on this video is how a simple discussion of a simple issue like microstuttering can just spiral out and lead to a discussion of every single visual aspect of what's on your screen when you're gaming, and one conversation just dovetails into the next. So I mentioned before about DLSS performance mode and how at 4K that way of rendering is not optimal. And why is that? I mentioned before, basically it's the 1% that can't catch up with the increase in average FPS, and that's essentially what's happening. But let's try to understand a little bit why that is. So in DLSS, what's happening is more of that traditional graphics rendering pipeline is being offloaded into your AI, into the tensor cores, onto the GPU. But the CPU always has some work to do in any game, and with DLSS, that work is increased. So what happens with DLSS is an increase in CPU draw calls. Draw calls are the geometry instructions that the CPU sends to the GPU. The GPU picks those up, but it's not rendering them in the same type of graphics pipeline. Rather, it's being offloaded to the tensor cores, and it's AI that's rendering it. But the CPU is being taxed. It cannot keep up with the demands of DLSS. And what happens is those 1% lows stay pretty much where they are, because at that scaling, now we're talking about DLSS performance mode in 4K, which means a jump from 1080p downscaling all the way up to 4K. And those 1080p, there's not as much information in that small render resolution for this rendering machine to work with. So the CPU's got to do a lot of work, a lot of draw calls, and the GPU is not picking up the slack in the same traditional raster way. Rather, it's offloading that workload onto the AI, which is just boosting frames, artificially boosting frames, and the 1% kind of stay where they are because the CPU is taking up more of that workload. And so it becomes less efficient at 4K, I'm talking about. So, and now what does ray tracing do? And here's what's interesting. I found this kind of interesting to think about. I try to come up with ways that are interesting to think about, because all of you know all this stuff, right? But maybe you haven't thought about it this way. I flatter myself by telling myself I'm introducing new ways of thinking to people for concepts that they're familiar with. Okay, so let's use the same color codes that we were using before in those bar graphs. This is native rendering, okay? Let's call this native. And that's your FPS in the blue. And over here in orange, we've got your, stop it here, your 1% lows. Now, let's do DLSS. DLSS performance mode in 4K. See, all the way over there. Really boosts your frames, right? Some of them anyway. And here are your 1% lows. And this is DLSS. I'll put performance mode at 4K. Because there's lots of implementations of DLSS that you can play with. What's ray tracing do compared to DLSS? Now, isn't that interesting? What ray tracing does compared to DLSS is the opposite. It's really the opposite. So what do DLSS and ray tracing have in common? They both exist outside of that traditional raster pipeline. I mentioned this with DLSS, how a lot of that workload is being offloaded to the AI. Ray tracing, let's go back to the last video where we were talking about drivers and APIs. So here's your graphics card, right? It has to communicate with your OS. It does so through APIs. And this, let's call this your traditional, I guess, raster pipeline. Okay? Think of ray tracing as a VM. As a VM, sort of sitting on top of this machine that is the traditional render pipeline. It's not part of it. But in the same way a VM does, it shares resources with it. And in the case of ray tracing, all of the resources of those extremely fast frames that can render these effects, because that's what ray tracing is. It's an effects machine. It's a simulation of natural lighting. So all of the frames that can render that natural lighting are being used by ray tracing such such that your average FPS just goes way down. But those 1%, they stick around because your 1% are kind of hanging out here in your traditional render pipeline, while your fast frames, I guess for lack of a better way to explain this, are being taxed with the heavy demands of ray tracing on the GPU. So both ray tracing and DLSS performance mode at 4K, but DLSS really in general kind of do the opposite thing. And that's really fascinating to think about when considering that they're both mentioned like in the same breath almost. So here's another thing that's fascinating that you could think about. Two opposites that you'd never think are opposites. I mean, like this other example, they're similar in many ways. Okay, they're not quite opposite. So opposites, but two opposites. VSync and G-Sync. What is the scenario in which we talked about one of the things you can do in graphics settings to address microstutter? Obviously, you can cap your frame rates to your monitor refresh rate. Okay, and that's what I did in the Red Dead Redemption to try to reduce the microstutters that might be present otherwise in that game. And that makes your frame times more efficient. It renders things on a consistent scale where your 1% lows are matching up, sort of syncing up with your FPS. But we don't want that if I'm playing CSGO, right? Let's say, and I never will be, but let's say I'm some kid who wants to, win one of these $100,000 tournaments, and I need the fastest response time. I don't care how pretty it is. I need to beat that guy. All right. And so every little nanosecond of input lag is costing me money. So if you're like that, you don't want to cap your frame rates, right? You want to render those frames. But obviously, a microstutter, even one, is going to kill you in that scenario too. So what do? Well, you've got some help. You've got some help in the form of these technologies. VSync, which preceded G-Sync. And you've got G-Sync. Came later. So, let's say we've got this issue of microstutters. Here's a great way to fix it. We enable VSync, and for the reasons I just explained, we're taking what might otherwise render average FPS, say 400 FPS, and we're capping it to the monitor's refresh rate, which, if it's my monitor, is 240. Because 1 hertz equals 1 frame, right? 1 hertz, here's your waveform. Okay, so there's your hertz. And the space from this crest to this crest is 1 frame. All right, don't say anything about that drawing. So basically just think of the frame as a box sitting on top of these two titas. There's your frame. You move it over here or over here, it falls down in the hole. 1 frame per 1 cycle, because 1 hertz equals 1 cycle per second. And FPS is FPS, frames per second. So 240 frames, that's it. That's all you will ever see. But I'm playing CSGO. I don't want to render 240 frames. I want to render 600 frames. How can VSync take those 400 frames and turn them into 250, 240 by increasing input lag. Why? Because when I click my mouse, here's where it responds. When it gets to the refresh rate that can drive it. But in G-Sync, where do you click your mouse? You click it right here. Within those 600 FPS, and it gets to the screen later. So in effect, it's like taking these 240 hertz and turning them into 600 frames, whereas V-Sync is taking your 400 frames per second and turning it into 240. They're the opposite, right? And I know they're not quite the opposite, but it's kind of an interesting way to think about things, okay? And I hope I've given you a few interesting concepts to chew on. Next video, we're getting down into the weeds, into the nitty-gritty. We are going to fix your microstutter. The fixes happen. Next video. I will see you then. Actually, I won't see you then. You'll see me then, because I'm the one making the video. Make your own fucking video. See you next time. Except not really.